Welcome to a new test and teardown video. This time it's another Tektronix. It's called 2101. It's a Pulsegenerator. And it can go all the way to 25 megahertz. And it was packed and shipped to me for free as a gift. So thank you very much, Søren, for supporting me and my channel. We really love all these things that people sent me, so thanks a million times. I was told this unit is not working perfectly fine in one of the outputs. So I will of course investigate what it does and was it this defect here in the output section. It looks a little bit like my datapulse units. So back in the 1970s, pulse generators like this with a positive and a negative output with individual amplitude and DC offset, that is obviously something you would use back then. This unit was released in 1970. And I believe my unit is from 1972. It was purchased by Rode Schwarz in Germany. So it was in their test division. So they probably used this to test some other equipment. We see this sticker here. It says maintenance in 1972. And next maintenance is in 73. And I believe what they mean by maintenance, I mean this is probably just a test and check or calibration check. It's funny they don't call it calibration, but that is how they did. And then they got a little inventory number here as well. And a test sticker as well. Okay, they love stickers. But I will give them a full point for not putting any stickers on the front. I really hate it when people put stickers on the front. I believe here at the back, those are probably power supply transistors. So this is a good way to dissipate heat here at the back. The voltage selector is one of the most beautiful I have seen in a long time. I should definitely open this and show you how beautiful that is. I think it's super unique. Let's try and open it. No? What? Why don't you? Okay. Ah, that is why. So the fuses, they come out. That is a really good way to do this. So that means now everything is safe and you can't stick your fingers in and touch the fuses because they're that deep in. So the idea is you have this little indicator pin that sticks out. And this will of course show you the low and the high. And then, okay, in the high, you have these three opportunities. So that means we can move this left to right. So this is low, medium, or high. And we are in the medium, so 208 to 252. So this is, we are the right place. I just wanted to show this, how beautiful it is. And they even repeated the voltages here. See? Ah, you can't even lose it. And then you rotate it. Dippity dip. That is so lovely. Somebody spent a lot of hours making this wonderful little piece here. And this one, you can't lose it. See? I mean, that is nice. When working with old stuff like this, and I really don't want to get hurt and all that. I know there is a little thing I want to show you here. So this is the German mode plug, so it doesn't really work in Denmark. So that means you're not going to get your chassis proper grounded. And the only leak I got is only a 2 nano from mains to chassis. And is this really connected to chassis? Yeah, I believe it is. No, it is not. Here we go. So this one is chassis. Okay, that proves this one is good. So let's turn it. So that will be my chassis AC voltage to a proper ground. So that's 60 volts on this one. You see it's quite high voltage, so if I push it, the voltage drops. I'm not quite happy about this. What if we measure this in a real high? Let's take the ground one from the voltmeter and just hold it in my hand and then measure. Okay, see? So it's not that bad. I just reversed the mains plug, and now it's 93 volts on chassis. So I need to change the mains plug to a proper grounded one, because when I plug in my scopes or other measurement equipment, I know I need to go and debug in this unit for a few hours, or probably even a few days, depending on the challenge. So I mean, we need to change this plug and do it a little bit safer. Here is something most people don't know, and they still do this wrong. So I really need to repeat this now and then. Every time I see this, I think we should repeat it. So the screws here, they're like insanely loose. Ooh. And I'll probably just do it like this and then pull. Okay, here we go. See, the problem is somebody tinned the wires. So when you tin wires and then you screw them in, then they just get loose because the tin kind of floats under pressure, and then you lose the pressure from the screw, and then you have a loose connection. So never ever tin something. You need to screw. While we are at it, why not tell exactly how to do it? So the real way to do is to twist the wires as hard as you can, and then start by making it double as long as you need. See, here's what they did. Twisted them very hard and then bend them back, and this way there is double the material to screw on, and it will get a good safe connection. And by the way, when you unscrew something many years later that is done like this, you still feel there's still a good stable pressure on the screw. So first let's just investigate a little bit what works and what doesn't really work. So the outputs here, that'll be channel 1 and channel 2 on my scope. This one here I trig on. That is the pre-trig output, and that is the top one up here, right? So what we can play with here is, this is the pulse duration. So if this one goes small, you see the tiny little pulses. I try to make it a little bit wider so we got something to look at, right? Let's just go down here. So this is the variable pulse duration. I take this all the way down. Then this way we are in calibration mode. This way we can trust the numbers that is written here on this scale. And the same here with the period time. So if I make this slower, see, we go slower, and this is the period. All this works. And let's look at the pulse. You can see, let me move the pulse a little bit down, so this is a little bit better, right? So if we play with the pulse, we want more pulse. The pulse gets smaller and smaller, and this is because the output is inverted. It is not as it is supposed to be. So if I crank this down, let's look at this is the red channel here. This is channel 2. This is the positive. This one was supposed to be a positive pulse, but it's a negative going pulse. So that is already really weird. And the other one is the same. This one is supposed to be a negative pulse. This one is negative, so this one is sort of at least the right polarity, right? So let's look a little bit on the way the things works here. We got internal terminations right there. So I took those two out because I got external termination. Otherwise, if I terminate here, nothing. Yeah, I get half the voltage, obviously. Yeah, perfectly fine. So this is supposed to be the amplitude of the signal, but it is, look at that. The DC point goes all over the place. That is not what you would expect. DC offset is, of course, DC offset. And we are now in, yeah, well, let's go down to 1 volt per division. And here is 0, okay? And this is, of course, the positive one. So this is the offset all the way down to a positive. And then I poke with the amplitude. Okay, let's take amplitude all the way down and then move around. Oh, here is my offset. So offset is supposed to be 0 here in the middle. See, we got negative and we got positive. I don't know if this is real easy to see on the video, but this is how it's explained on this and here. So there is definitely a problem with DC points in the entire thing. The other one is doing exactly the same. So it's probably a power supply issue or something like that. Weirdo issue here, huh? It is, as always, so beautiful inside. Look at the circuit board in gold plated instead of solder mask. I really like that. That will be the 2 output amplifiers. We also got some additional power output transistors just like this on the bottom side. See, that will be all the complete signal path for the 2 output channels. They're using a little bit different transistors, obviously, because it's NPN, PNP sets. Got some rectifier bridges, the main capacitors, power regulator transistors here on the back. Got a little bit of power supply stuff going on here. Oh yeah, that will be the timing switch for all the settings right here. And that will be the delay switch. And those are absolutely fantastic. They're so specially designed. And I believe they also use them in their high-end oscilloscopes. And they use a special contact system that interface directly to the circuit board. Circuit board design is from 1969. That was a giant leap for mankind that year. And here is the bottom side of the circuit board. And exactly like I said, output power transistors located really close to the output. Obviously because of the rise times and the high frequency. This one can do 25 megahertz. So obviously this is how you want to do it, right? And I think you can really see this through the circuit board. That will be the contacts for the switches, like I said. Very special stuff. And since I'm really lucky, all the frequency ranges and all that seems to be working, so I really don't want to open this because we got little springy things and this is impossible to assemble this if you don't know what you're doing. So please don't pull these apart if you don't need to. And here is the delay switch. I of course got the full manual with all the measurement points and all the how to do this and how to do that. And here is all the voltage supply checkpoints. And on the next page I find this nice little voltage checkpoint table, and I ran through all the voltage, and they are within specifications, as you can see here. So all that is perfectly fine. It's not a supply voltage out of spec kind of thing. So what we can do is take the little thermal camera and look at the two output channels side by side. And you see here is a very, very big difference in the two output channels. We got some very hot points here in one of them, and we got some very cold ones in the other one. And even there we got some nasty stuff going on right there. I mean, there's absolutely no balance whatsoever. Nothing here looks the same. And we got some really warm parts. That will be one of the resistors. And oh yeah, here is also a very warm resistor, but that is what I could expect. That is some power supply resistor. But look at that one. 180 Celsius. This can't be good. So what is this resistor doing? Yeah, but I got a lot of stuff that is wrong in the entire output system here. It even smells a little bit warm. I'm actually really happy about this. So now I have cured this unit from its insanity. This is so funny. Look what we got here. Just some BC 557s in the PNP section right there. Because all of those PNP transistors, they were like more or less completely defect. So now this unit is doing like this. So that will be the trigger signal. Look at the two outputs here, right? So if I play with the output level is level. If I take the same channel and play with the DC offset, DC is something completely different than level. And both of them, they do this now. Haha, man. And here's the DC offset. So it was all the defect stuff in one channel that affected the other one from working in the DC as well, because of course all this stuff here is DC coupled and whatnot, right? I want to show you the PNP transistors. Let's play a little bit with them. And they were all four supposed to be the same. Here is some unoriginal. This one is an NPN. Well, that explains about something here not working. The inverted features of one of the channels. Oh my god. So here's my trustworthy little transistor tester. Let's look how we test these, right? It was supposed to be collector, base, emitter, and this is pin 1, 2, 3. Okay. Pinout seems to be alright, but what is this funny diode? This is not supposed to be there, right? Okay. Let's take another one and do exactly the same. See, I'm not turning and swapping or rotating anything here, right? I'm just plugging it in exactly like the other one, right? So it's supposed... Oh dear. How is that possible? It still says PNP, but oops. Pins completely rotated. What the... How's that possible? And they got the same name and number on them, right? Hello. The other one's not better, but this is... How is this possible? There's another little annoying thing about these sockets. The pin dimensions. When I take the new transistors here, I can't really stick them into the sockets, so that is a little bit annoying. So I'm still playing a lot with this thing and the different performance settings and all those kind of things. So let's try and see what happens. Yeah, I got, of course, a pulse that is a lot shorter than the repeat frequency. And this is only 2.4 megahertz of repeat. And if we see the yellow curve, it's overshooting and it's looking a little bit weird. This is that channel here, and this is of course the channel I've been poking around with the transistors, but at least it is working so far. I just need of course a little bit different PNP transistors that matches a little bit better their performance, but that is definitely why it is looking a little bit like that, right? So also if I adjust the pulse is too short, the time is too short, so I don't get that pulse. I really like the way that everything is completely individual, and so here's my pulse width and here is my repeat. And if I go real slow, and oops, see, and then I go the slowest, but here, and then the slowest goes fast again. Look at that. So we go down, down, down. That is faster, 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 faster. See, the fastest is the same as the slowest. Is that supposed to be like that? It's because I go outside of the range and then it goes into some other funky mode, right? So that explains it. But anyway, I don't want to make this video any longer. I just want to say thank you very much for watching. And that was another fantastic Tektronix. I think this will be number 19 Tektronix video. So thank you very much for watching. Please come back real soon. All right, bye bye.